pre-calculus. So hopefully you had a chance already to do something similar to this at the beginning of class. Um, we've got a table on this graph at 2, 3. So there's already a dot there. And imagine somebody pushes it around the room, just draw an arrow, start from the dot, draw an arrow, and show the push, right? So I'm going to push in green. Blam. All right, we probably do something different than me. Um, cool. Good job. Well, today we're going to look at vectors, and um, the learning target is going to be that you will be able to find the component form of a vector. Because we probably don't know what any of that stuff means. What's a vector? What's component form mean? So how will we know when we got there? So let's think about this table getting pushed. This kid, here's a kid. He pushes the table around. You can if we think about all the different possibilities, right? I mean, for the kid to push the table, there's an infinite number of possibilities, right? Um, so the kid can push to the left, you can push to the right, you can push it up, push it down, forwards, backwards. Um, there's all these different directions, like we could push this direction, straight up towards the front of the classroom. That would be one possibility. If we want to think about all the different possibilities, what if you pushed it just a tiny bit over to, towards the left? Just a little bit more, maybe just a little bit more. We could say every one of those is a different possibility. What if you just barely pushed it, like a level 1 push, in this direction, and then as a different possibility, what if you pushed it a little bit harder, and we might call it a level 2 push, still in that same direction. There's a lot of possibilities, you know. Um, and so really what that comes down to is it's an example of a vector, right? So in your notebooks is something we want to keep track of. Write this down. A vector is a quantity that has both direction and magnitude. If you watch Despicable Me, you remember that vector was the why they randomly put math into Despicable Me, but a vector quantity that has both direction and magnitude. So if we think about the kid pushing the table all over the room, all the different possibilities can be captured by just saying, well, if we change the direction, that's a different possibility, and if we change the magnitude or the size of the push, then that also creates a different possibility, right? So there's a ton of examples. I mean, pushing a table would be an example of a of force. You could think of like an electric field or a magnetic field is going to do the same thing. You have a magnet that's going to pull on some iron filings or something. Well, if you have the magnet over here, it's going to pull this direction. But if you move the magnet over here, it's going to pull that direction. You've changed the direction. If you hold it closer, it's going to pull harder. If you have the magnet further away, it's not going to pull as hard. So there's a ton of examples. This shows up all over the place in physics and science and math. And in fact, it showed up in the one assignment the other day. So a vector, any vector described in two direct dimensions, like an x dimension and a y dimension, can be thought of having an influence in two different directions, right? And which is actually what we did in the escalator problem. We looked at those two different directions. We looked at just the horizontal component and just the vertical component. And then we can say each part of the two-dimensional vector is known as a component, right? So there's another vocabulary word. The components of a vector depict the influence of that vector in a given direction. So if you've got something going like diagonally, let's say the kid is pushing the table diagonally, so we could say, yeah, he pushed it diagonally, but we can break that apart into how far sideways did he push and also how far vertically did he push. And so we can take those two pieces of the push, and even though it actually moved diagonally across the floor of the room, we can look at the two different aspects, how far in the x direction, how far in the y direction. So the combined influence of those two components is equivalent to the influence of the single two-dimensional or diagonal vector. And consequently, the single diagonal or two-dimensional vector could be replaced by the two single dimension, the x component and the y component, right? Okay, so a vector is a quantity that has both direction and magnitude. So I have two arrows here. This is the graphical representation of a vector. It's an arrow with just an arrowhead at one end. So these both have the same length, they have the same magnitude, right? But obviously they're pointing in different directions, so these are going to be different vectors. If I had another vector that was going in the same direction, but it was a different size, that also would be a different vector. Okay, so we have some vocabulary words I want to look at related to vectors. So here's my example of the vector going in the same direction, but with a different size. Um, so vocabulary words: initial point, that refers to the starting point of the vector. I'm going to get rid of these other guys. Let's just look at this. Let's get these all the way off the screen so we're not confused by them. Let's just look at this one. Great. Okay, you saw it. So an initial point is where it starts from. So maybe we'll start with green. Okay, that's the initial point. It's the starting point. The terminal point, that's where it ends. So the arrowhead represents that's the direction that's moving, and so that is the ending place right there. Magnitude. Oh, that's the size or the length of the arrow. I'm running out of room because my bad handwriting is taking up too much space. And the direction, that's the direction that it points. I don't know how else to describe that. And then lastly, the component form. Um, so we just talked about that actually on the previous screen. If you take any diagonal vector, any two-dimensional vector, you can look at the horizontal aspect and the vertical aspect. Okay, so those are the components. So there's a special notation in math that we use to write that. It's called component form. We'll take a look at um, in this next slide. So component form of a vector always uses pointy brackets. So it's going to look very similar to the coordinates of a point, but coordinates have round parentheses and vectors are written with pointy, pretend my hands are those pointy brackets. So always written with pointy brackets. I don't think they have a special name. They're called vector notation. So we're going to put the x component first and the y component first. It looks very similar to the coordinates of a point, like I said. So in this example, it says find the component form of this vector. Well, what I need to do is start at the initial point and I want to know how far sideways it goes. That's the x component. All right, so that was how many spaces? 1, 2, 3, 4. That's 5 spaces. So there's 5 spaces. And then I want to know how far does it go vertically? Well, that's 1, 2, 3 spaces. It's going down 3 spaces, and the graphing notation down is always going to be a negative. Pointy brackets separated by a comma. Okay, whoa, man, that was a yikes. Well, don't cross off half of your components. If I can get rid of it. Okay, we'll just keep it. Don't cross off half of your components. Let's, how does it keep ray? Oh my gosh, what is it doing? I'm just gonna get rid of the circle. There, okay. So component form only, it does not capture every single piece of information about this vector, right? The location of the vector on the graph is not actually captured by component form at all. So if I had moved the vector to start at a different initial point and a different terminal point, as long as the horizontal component remains the same and the vertical component remains the same, the components do not change. This vector is still 5, -3, whether I draw it here or whether I draw it here on the graph or whether I draw it here on the graph. All of those vectors are going to have the exact same component form, right? So location is not part of the definition of a vector, right? The only thing that is part of the definition of a vector is just direction, magnitude, right? There's no mention of location in there. Okay, so here's another example. Here's a green vector. It's got an initial point. It's got a terminal point. What is the component form of this vector? So I'm going to go side. I don't want to move it. Computer's not cooperating with me. So I'm gonna go sideways by 3 spaces. I'm gonna go vertical by 2 spaces. Those are not straight lines. Well, okay, pointy brackets. Oh my gosh, look, there's a red vector down there. What's the component form of the red vector? Well, this one also goes sideways by 3, and it goes up by 2, and so that has the same component form. Okay, do the red arrow and the green arrow represent the same vector? Yeah, they do. Are they, if we asked a different question, I mean, are they, in the same place on the graph? Well, no, but that's not part of component form. That's not one of the aspects we look at when we're describing a vector. We can look at it. It's not like you can't ever describe the location of a vector, but it's not part of the description using component form. Okay, so we have some more examples. Like I think I'm going to skip through these. Based on the vibes I'm picking up through the video recording here, I think you've got the component form and graphing under control. So other ways we can find component form. Sometimes we are actually given coordinates for an initial point and a terminal point, right? And in that case, we can still find the component form. We just need to get rid of the coordinates and find what is the horizontal change, what is that vertical change, so we can just focus in on the component form. But if we are given coordinates, if a vector, this is called the head minus tail approach. If a vector has initial points, some x coordinate x1 and a y coordinate y1, and a terminal point at x2, y2, whatever, I mean, those can be some coordinate numbers, obviously, then its component form we find just by subtracting the x coordinates. So we're going to start with the tail. That would be the terminal point. That's where the pointy part of the arrow is. Start with that x coordinate, subtract the x coordinate of the initial point. So the end minus the beginning, terminal minus initial, head minus tail. Right? And then you subtract the y coordinates, start with the terminal point first, and then subtract the initial point. Okay. So maybe you're thinking, that seems familiar. I've seen that someplace. You've totally seen that someplace before in a previous math class, several previous math classes would be my guess. You remember what it's called? Where is that from? Yeah, it's from the slope formula. If you remember, the slope formula is y2 minus y1 over x2 minus x1. This is like super, super similar. And when we were finding component form on the graph up here, I was basically drawing like these little slope triangles like you learned in Algebra 1, right? So component form has a lot of similarities to slope. Obviously, we use it differently, and it is describing a vector, not just some line, right? But there are a lot of similarities, and don't write it as a slope fraction. This is not slope, so we've got to make sure we always have those pointy brackets and comma to separate the coordinates. So maybe we'll just try one of these. Find the component form of a vector from the initial point 5, -1 to a terminal point -2, 4. Okay, so these are coordinates of points. If I was to plot that on a graph, that's just a dot, and this one is just a dot. Right, so I've got the parentheses there. So if I'm going to do head minus tail, I'm going to start at the terminal point and then subtract the initial point. So I'm going to do the x's first. These both circled. Okay, so -2 minus 5. And then we'll do the y coordinates, 4 minus -1. Didn't change colors. Okay, well, I guess it's green. And then probably I'm stuck. Oh, no, it changed now. Okay, so -2 minus 5, that's -7. And 4 plus 1, 4 minus -1 is 5. Okay, I want to try to circle that because last time I circled it, it didn't work very well. So I found the component form. And if I wanted, I could pull this graph over. You could always graph things. That is an option, right? We have lots of tools at our disposal. If you wanted to plot the points onto the graph, on a piece of scratch paper or a piece of graph paper, and draw out your little slope, try and draw your vector and your little slope triangle, and count spaces on the graph paper, the totally would do the exact same thing. Um, so I have I'll do the terminal point in red because I got my red first. So -2, 4 is right here. My initial point at 5, -1 is right here. Starts at the green one, ends at the red one. That's not too bad. I was thinking that was not going to be straight at all. And so I went uh, in the horizontal component. I go 1, 2, 3, 4, 5, 6, 7 spaces. So that's the -7, and then 1, 2, 3, 4, 5 spaces up. And so that is the 5 for the y component. So I can do the same thing no matter which of those approaches I use. All right. Well, that is the lesson part. So I bid you adieu, and